Good morning, guys. So, I hope you are all okay. Yesterday, we discussed about one of the very most important problems in steel design, that is the eccentric connection. If a eccentric load is acting on a beam column joint, what is the effect of the load that we have designed? But we have designed only bolted connection. We have seen that in a bolted eccentric connection, there are generally three type of connection in an eccentric connection that you have seen, that the normal framed connection, second is the seat connection. In the seat connection there was stiffened and unstiffened seat connection, and then we discussed about bracket connection type 1 and bracket connection type 2. But yesterday in the last class we have designed all that through only bolted connection, but today we will be designing with the help of welded connection. That we know that two type of connection is in our syllabus, bolted connection and welded connection. So today we will be designing the connection with welded connection. So similarly, if we see that the welded eccentric connection are generally also three types. So welded eccentric connection also are three types. Flexible joints, we are all in our study we will always use flexible joints. We will not use moment connection, that is semi-stiff or semi-fixed or fixed connection we will not use. So we will only use flexible joints. That in the flexible joints, similarly there are three type of connections: bolted frame connection, welded frame connection, welded seat connection and welded bracket connection, as in the case of normal bolted connection also. But here we will be designing the welded connection. So when we are designing the welded connection, the first thing that we need to design is the weld, that is the size of the weld. Okay, we have to determine what will be the size of the weld for the connection, that we have to determine. So that will be our basic motto, to design the size of the weld. Now various connections require various type of forces, various type of moments will be acting on the connection due to the reaction force. We will all consider that, and then we will determine the welded size of the weld for the connection. So first connection for today, our lecture, is the welded frame connection. So welded frame connection. So in the frame connection, as in the same in the case of the bolted connection, the beams are connected to the column or other beam. That is the here in this picture you can see it is a column flange. This is the column flange and the connecting beam is there. The column flange is connected with the column beam by means of framing angles. So these are the framing angles. Here is one framing angle and there will be another framing angle. A pair of angles or plates are placed on either sides of the wave of the beam, that are the framing angle, to be connected. Now for extra connection, a seat angle that needs to be here also. Seat angles are provided only for erection. That means only for erection means only for placing. That means when the beam and the column will be connected together in the frame connection, only then the seat angle will be used. But after the erection process is over, that seat will not be here, so it will be removed. Okay, so it will be removed. It will be removed. Okay, so so we only need to design this welded connection only. So we have to determine the size of the weld for that connection. And okay, so this is the welded frame connection. All the things are given here: column flange, the connecting beam, framing angle with welded connection that we have to design, and the erection seat that will be removed, that may be removed after the process is done. Then coming to the design procedure. What is the design procedure that we need to consider? Now the vertical reaction acts here. Okay, the vertical reaction V on each weld. So here is one weld and here will be another weld. The vertical reaction all weld is calculated by V is equal to R by 2. R is the reaction acting here. So R is the reaction acting here. So V is equal to R by 2 for each weld. So there will be two welds. So R by 2. That's why. Okay. Now the vertical shear. Now first we need to understand something. There are two connections. One connection is welded connection with the angle. So this is one connection and this is the second connection. So first connection with the one leg of angle with the column flange, and second connection will be another leg of angle with the connected beam. So for the both connection we have to determine the size of the weld. So the process will be followed through, but this is the basic theory, basic funda. How can we determine the size of the weld? there will be two sides of the weld. One weld will be for the column flange and another will be for the connected beam. So, to design for all that. Now, the vertical shear per millimeter length for the weld QVS and the horizontal shear per millimeter length for the weld QVH, connecting the angle to the column flange. So, first we are determining this connection. Okay, I did a computed vertical shear per millimeter length per weld, that is equals to QVS, V by T, V we have calculated, and this is the V of the angle. Okay, one angle length is D, that is the length of the angle we have to determine first. So, D is equal to the length of the angle. So, horizontal shear will be 1.8 into R into E1 by D1. Now, coming to the term E1. What is E1? Now, in the beam flange column flange connection, this is the vertical shear that will be acting. Okay. Now, what is the meaning of E1? E1 is the distance between the end of the connected beam to the center of the point root. Okay. So, value of the E1 will be BF by 2. This whole section is BF, so it will be BF by 2. Okay, so BF is the flange width of the beam, so we can calculate the E1 from here. Okay, so this will be E1. Now, the resultant shear force we have to calculate. The resultant shear force, the V1 we have calculated, vertical shear QVS is we have calculated, D will be is the length of the angle. Okay, the resultant shear force QV is determined by the following formula. It should be less than always that Fu by root 3 gamma mw. Now, what is the meaning of gamma mw? Gamma mw is equal to, as we know, 1.25 and 1.5, either 1.25 or 1.5 depending on the type of weld. Is it shop weld or is it site weld? Okay, depending on that we have to choose the gamma mw. Now, so we have calculated the resultant shear. Now, how the weld, now we have to determine the size of the weld. Now, how the size of the weld is determined? Now, strength of the weld is determined per millimeter length. That is the formula for the strength of the weld. You know that if you can recall, this is the strength of the fillet weld. Generally, we provide fillet weld, okay, and then it is equated with the resultant QE and the size of the weld is determined. So, QE is equated with the strength of the weld. Here, length of the weld we know, we can determine the length of the weld here. We can determine the length of the weld. This will be the length of the weld. We can determine that. TT, that is the throat thickness, we have to determine. If you know, MW we know. So, from the TT is equal to the effective throat thickness, that is equal to 0.7 into S. So, S will be equals to TT by 0.7. So, the TT, if we know the TT, that is the effective throat thickness for the fillet weld, we can determine the size of the weld. Okay. Then, so this connection is done. So, connection for the column flange with the angle is done. Now, coming to the connection for the beam. So, for that, the CG of the weld group connect the angle with the wave beam is determined. What is the CG of the? So, let us erase all that. Okay. So, the CG of the weld group. So, if this is the connection between the wave of the beam and the angle, so this will be the CG of the weld. We have to determine. So, first we have to determine the CG of the weld. So, from here the CG of the weld is we have to determine. Then now the weld connection of the angle to the beam is to be determined. How? So, here also we have to determine the horizontal shear in the connection to the wave of the angle. QVH equals to V into E2 into R, it is equals to VR. What is the meaning of R? R is the distance from the CG of the weld group to the extreme weld position. So, this is here, from here to here. Okay, let me first clear up. Okay, so this is the CG we have got. This is the CG of the weld group and this is the extreme weld. So, between that distance is the value of R. So, we can determine here. I have also mentioned this is the R. So, R we have to can be determined. Okay. So, R V we know E2, that is the E2. Now, what is E2? E2 is the end from the end of the end of the column flange to the end of the end. So, the total bearing length plus the total bearing of the column. So, this is the E2. We have to determine the E2 value. We have to determine the E2 value and put it here. So from here we can determine the value of the E2. Now what is the value of the so QVH equals to V into E2 into R. Now J, what is the meaning of J? J equals to now J equals to IP into TT, that is the throat thickness. Now IP we know, IP is equal to IX plus IY of the weld group. So we can determine the IP, that is the IX of I of the weld group, and TT. That T2 we have to find out. So vertical shear QV is equal to V divided by V into TT 2A plus TT. So from here we can determine the value of the vertical shear also. Now here this TT term and this TT term are unknown. So from here we have to determine the throat thickness. So the resultant shear will be that value. So the resultant shear from here we have to determine the. Now we have calculated the value of the QE, that is the resultant shear force, from these two formulas QVH and QVS. From here, using this formula, we have to determine the value of TT. So similar, from here also we can determine the value of the size of the weld. Similar in the case of the previous formula also. So S is equal to we can determine. So from here we have to determine the value of the TT. Here TT is unknown, so we can determine here all are known, so we can determine the value of TT. This is the welded framed connection. Okay, so you have to determine all that with the help of this. Okay, now so these are the steps that need to be followed. Now in your book no example is there, so I haven't given any example for the welded frame connection, and welded frame connection is not that much important because bracket connection is there. Always the map comes from the bracket connection and the seat connection. So we will be designing the seat connection and the bracket connection first. Okay, now coming to the seat connection, welded seat connection. In the same case of the bolted connection, welded seat connection is also two types: unstiffened seat connection and stiffened seat connection. What is the meaning of unstiffened seat connection? There will be no extra stiffening bar. Okay, in a welded unstiffened seat connection, there is the unstiffened seat connection. Two angles are used. Two angles. One is the seat angle. One angle is welded to the column which acts as a beam seat, that is the seat angle, and a cleat angle of nominal. So this is the nominal seat angle we need to provide here. Okay, here the cleat angle dimension is nominal. So nominal cleat angle is provided here. So the seat angle is used. We have to design the seat angle here, and in the cleat angle, a nominal cleat angle, that is the 100 into 100 into 6 is provided. Now we have to design the cleat angle and the weld here. So as you have seen in the previous lecture, that is the design of the bolted seat connection, here we have also designed the seat angle for the normal unstiffened seat connection. Here also the seat angle has to be designed as well as the welded connection. So here in this picture you can see this is the cleat angle that we don't need to design. This is the value of the seat angle. We have to design that. This is the weld. This is the value of the weld. We have to determine, and this is the seat connection. Seat angle we have to design. Now design procedure for the welded unstiffened seat connection. The design procedure of the bolted unstiffened seat connection is followed. That means there is no design differences between the welded and the bolted seat connection. So the seat connection design is followed as in the case of bolted. Step number 1 to 5 is same. Now let us open the bolted seat connection formulas. So let us open the so we have opened the normal bolted seat connection, unstiffened bolted seat connection formula here. We have opened the unstiffened bolted seat connection formula here. Now first all the procedure will be followed. So design procedure first we have coming. Okay, so the design procedure is for unstiffened connection is same. So coming to the design procedure for the unstiffened bolted connection, that is the first we have to determine step number 1, that is the length of the wave bearing. Okay, length of the wave bearing has to be determined. Okay, the first procedure is length B of the seat angle is assumed to be equal to the width of the beam flange. Here the length, so say here it is similar here also, the length of the seat angle is assumed is taken equal to the flange width of the beam. So if we know the flange width of the beam that will be provided to us, we can determine the length of the seat angle. What is the length of the seat angle will be here? That will be the length of the seat angle, B value. That will be the length of the seat angle, Okay. Now coming to the step 2, that is here also same, that we have to the length of the wave bearing by the similar formula. What is wave bearing? That is the bearing of the wave from here to here. How much bearing is needed? That is the length of the wave bearing. So B we have determined from that formula. Here it is also same. Okay, now coming to the where R is a reaction from the beam and T is the thickness of the wave of the beam, that is the wave thickness of the connecting beam. Similarly, the outstanding leg, so similarly here from this value, the outstanding leg that to be used as sitting leg is assumed. That means that leg, it is to be the sitting leg, the outstanding leg, it is to be the sitting leg. So the outstanding leg is determined through this formula. So it is similar to that formula. Okay, by the how to do that? That is using this formula here. So here we can use this formula. So determining the outstanding leg, we can use that formula. Now coming to step number 3. So, length of the bearing on seat, that is B1, that is equals to B1 equals to B minus RF. It is similar here, B minus R1 plus TF, where R1 is the root radius of the beam and B2 is equal to B1 plus C minus TA plus RA, that is the B1, B2 is equal to B1 plus T minus TA plus RA. From these two value we can determine B1 and B2 both. Then so where B2 is equal to TA is equal to thickness of the angle that we know, and RA is equal to root length of the angle that we will determine, we will get from the code, that is the ISSP6. Now here also step number 4, connected leg. Now in this step, so chosen that at least 2 rows of horizontal rows of bolt can be accommodated. Now here that step need to be determined. Why? That step is not need to be determined. Why? Because there will be no bolt connection, so weld connection, so there is no need for that step number 4. Coming to step number 5. Step number 5 is similar. BM at the critical section is determined. This formal formula. This formula is given here. R1 R into B2 square by 2 into B1. Similar formula here is used. Moment capacity, that is equals to 1.2 ZE5 by gamma M0. Here Z is equal to 1.6 into B into TA. P is equal to the length of the angle. That is the length of the angle and then TA, that is the thickness of the angle. So always the MD greater than MC, that is the always the moment capacity should be greater than the critical moment. Okay, if it is not, then the angle to be redesigned. Okay, so up to that, this is the normal design procedure that to be followed for the angled connection. Design procedure for the seat angle. So we have designed the seat angle. Now we have to design the connection, that is the weld connection. So we don't need to use that thing now. We don't need to use that thing here. We don't need the design procedure now for the connection. Okay, so let us cross that. Okay, now coming to the design procedure, the welded connection. We have to design the weld connection. So how to design the weld connection? Then, so first the strength of the weld is determined. Now the strength of the weld, LW, we can determine. LW is the length of the total effective length of the weld. This is the length and this is the length. This is the two length of the weld. So we can determine the length of the weld from that connection. Then we know the FU, that is the value of the 410, normal 410 for FE 410 steel, and a gamma M0, gamma MW, that we know 1.5 and 1.25 depending on the either it is shop connect or shop bolted or side bolted, or shop welding and side welding. Okay, now TT is unknown to us, so we have to determine the TT, that is the effective throat thickness. Effective throat thickness K into S. So generally K value is taken as 1, we will take the K value as 1 here. Okay, as per the rule, thumb rule, the K value will be taken as 1 here. Now we do not know the size of the weld, so we determine the size of the weld. How to determine? The value of the strength of the weld will be equated with the reaction force that will be acting. So if we equate the reaction force with the strength of the weld, we can determine the size of the weld. From this equation, which is the PdW is equal to R, from this value we can determine the size of the weld. So here the S is determined, and now for the as I have told you, the cleat angle is a nominal cleat angle used. Okay, 100 into 100 into 6. Now generally two numbers of 20 mm diameter bolt if you use bolted connection for the cleat angle, and if you do not, we generally provide that S determined here as the connection of the cleat angle also. Okay, if you now stiffened seat connection is generally similar to the normal bolted connection, stiffened seat connection. So no example has shown here. If you want to do an example, you can use the example that I have done in the normal stiffened seat connection as a welded connection. You can design that connection here also, but using a weld connection. Okay, now the most important is unstiffened seat connection. It is the very important. Now for a stiffened seat connection, a built up T plate is used. So this is the built up T plate. Okay, very much important, built up T plate. This is the built up T plate that has been used as a stiffener plate here. Okay, stiffener plate. Okay, and used for stiffener plate, and for seat operation a seating plate is used. So this is the seating plate and this is the stiffener plate. So generally a two plates are connected together by built up, two plates are connected together by a built up member and used as a built up T section as a stiffener plate. Okay, now here, and also a nominal cleat angle is provided, 100 into 100 into 6. It is the nominal cleat angle that is to be provided, and provide the flange of the built up T plate acts as a seating plate. So this is the flange of the built up T plate which act as the seating plate here. So this is the seating plate, that is the flange of the built up T plate. Clear? So this we need to design this built up T plate connection. Okay, now the design procedure. The design procedure of the welded stiffened seat connection is near about same for the unstiffened stiffened welded seat connection, except here a seat plate is used replacing the seat angle, and also a stiffened plate is used. So here the only difference is that in the place of a seat angle, a seating plate and a stiffened plate, that is the combined built up T plate is used. So we have to design for that also. So first the bearing length of the seat plate is determined, which is the same formula as in the case of here. The bearing length of the web bearing is calculated, that is the same formula. Okay, so B is equal to R gamma W by TW into FYW, where TW is the thickness of the connecting beam. So we know the connecting beam, so we know the thickness of the connecting beam. We can use that to determine the B. Now the length of the seating plate, very important part, coming to the now this is the bearing length of the seating plate. The length of the seating plate then assumed, and it should be the length of the seating plate. That means the length, that is the length of the seating plate. Okay, that is the length of the seating plate, that is equals to B. It is the length of the seating plate. All right, this is the length of the seating plate that to be used. So this is the length of the seating plate, B. Okay, now the length of the seating plate, what it is there, the length of the seating plate then assumed, and it should be greater than B plus C1, where C1 is the extra clearance to be used. So this is the extra clearance to be used. Okay, this is the extra clearance to be used. So B is equal to B1 plus C, that is to be given here. Now C1 is the clearance. Now step number 2 is width of the seat plate. Now we have to determine the width, that is the width of the seat plate. This is the width of the seat plate. So width of the seat plate equals to width of the beam flange BF, which should be greater than or equals to width of the beam flange or BF. This is the first case. Then, and the thickness of the seat plate equals to thickness of the beam flange or TF. So it should be greater than or equals to thickness of the beam flange or TF. Okay, this the same step number 2. Therefore the size of the seat plate is considered for the above value. So we have to, so we know the width of the and thickness of the seat wing plate, that is this plate. So we can determine, so we can select the seating plate here from. Now the thickness of the stiffener plate. Now coming to the thickness of the stiffener plate, this plate we have to determine. So thickness of the stiffener plate should be greater than the thickness of the wave beam. So beam of the wave we know, so from the beam of the wave the thickness of the stiffener plate is calculated. Now coming to the depth of the stiffener plate. Now the depth of the stiffener plate is determined from the buckling criteria. Now what is the buckling criteria? Depending on the buckling criteria, let us open IS 800. Okay, if we see, okay, this is the buckling criteria. Okay, let me go through that. Okay, so this is the buckling criteria. Classification of the cross section. Classification of the cross section depends on the buckling criteria. Okay, classification of the cross section depends on the buckling criteria. So depending on the buckling criteria, there are 4 buckling classes. As we know that there are 4 buckling classes: buckling class 1, buckling class 2, for buckling class 1 for plastic, buckling class 2 for compact, buckling class 3 for semi-plastic. Now as we are using here, it is shown that we have to use the depth of the stiffener plate from the determination of buckling criteria. So first, d by t, that is the depth of the stiffener plate by the thickness of the stiffener plate, should be less than. Now here comes the table number 2, limiting width to depth thickness ratio. Here it is a stem of the T section. This is the stem of a T section. This is the stem of a C section. For stem of a C section, we have to use these values. Which value to be taken? Here, as a thumb rule, we will use this value to be the required value, 18.9 epsilon. So d by t should be less than 18.9 epsilon. This is the maximum value. It should be less than that. D by t 18.9 epsilon. Where as for here it is written also from IS 800 for stem of a T section from table number 2 and semi-compact section. Here where d is equal to the depth of the stiffener plate and t is equal to thickness of the stiffener plate. So as we are using a built up T member, so for the stem of a built up T section, we have to use that thing. Okay, so that value for a semi-compact section we have to use. Now, so we do not need that now. Okay, coming to back in this formula, so we have to do the d by t. So from the here d can be determined. Okay, now here, so we have determined all that, the depth and thickness of the stiffener plate and the depth of thickness and of the seating plate, both are determined. Now coming to the distance of the end reaction from the outer edge of the seating plate is determined. Now as this is the bearing value B, this is the value of the web bearing. It is assumed in case of stiffened connection that the reaction force is acting at a center point of the bearing. Reaction force acting as a center point of the bearing. Now the distance of the end reaction from the outer edge of the seating plate. So this is the seating plate and this is the outer edge of the seating plate. So from here to here, the distance we have to determine. That distance is equal to E. So what will be the distance? It will be if the length of the seating plate that we have determined here, B, if we know the value of B, we can from B, if we subtract B by 2, we can determine the value of E. Okay, if we know B, this is B, okay, and this is E. So we have to determine the value of the E. That value we have to determine. Okay, let us clear all the things. Okay, so here we have to determine that value, that is equals to E value. Okay, if we need to determine the E value here, this is E. So this is total length is B and this length is B, total B. Now that value is acting as a center of the reaction. It is assumed that it acts in the center of the bearing. So this is B by 2 from here to here. So if we minus that, we can get that distance E. Now therefore the bending moment which acts as the end, it's calculated R into E, that is the reaction force that acts here as a reaction force into the E, that is the E value. Now the weld connection has to be designed. So bending moment has to be determined. Now the connection of the weld. Now the weld connection to be designed. So first the NA, that is the neutral axis depth for only the weld to be determined. This is the weld connection. So the neutral axis depth now determined. Now for that the thickness or the size of the edge to be assumed. So we have to first assume the size of the weld. Okay, then for example, now before consider, this is the example where this is the BP is equal to the thickness of the plate, seating plate, TP is equal to the thickness of the seating plate, D is equal to the width of the stiffener plate, and TSP is equal to the thickness of the stiffener plate. Now for taking moment at the bottom, we are determining the Y at the bottom. So using the you know how to determine the neutral axis depth. So you, by using this formula, we can determine the value of the y1, that is the y1, that is the value, and y2, that is the value. Okay, y1 and y2 is determined. Okay, y1 and y2 is determined. Now so one mistake has been done. Taking moment at the top, we have to determine the moment at the top. So from the top, if we here we have to determine the moment. Okay, so first for that weld length, this is the value, and for that this is the y1 plus y2. So from here we can determine the y1. So y2 will be total y2 will be total d minus y1, that we can calculate. Now Ixx of the weld group to be determined with respect to the CG distance. So Ixx, that is the xx value. So the Ixx will be determined. So only for this weld value, this is the first weld, this is the second weld. So for the only for the weld, we have to determine the moment of inertia. So from by Ixx is determined. Now if we determine the Ixx, now we have to calculate step number 6, the vertical shear, that is the R divided by 2 into D into Tt. The Tt we don't know, we have assumed the value of Tt. Okay, we have assumed the value of the Tt, and Bp minus Tsp by Tt, and horizontal shear by this formula, where Tt into Ixx we know Tt. Now R into E, R value we know, and E we have calculated, and y1 dash we have also calculated. So from here the resultant stress now to be determined by this formula, Fy by root 3 gamma mw. Okay, gamma mw 1.25 for the shop welding. Okay, we know that. Now from the above written equation, the size of the weld is determined, that is this formula. So size of the weld is determined by that formula. Okay, so nominal angle, as in the same case, is used. Okay, now coming to the one example. Design of a stiffened stitch connection to join ISMB these two value transmit an end reaction of the 320. So let us open another duplicate sheet here. Let us open another duplicate sheet here. Okay, so first all the properties are written, that is these properties are written, that is for Fe410, Fy is equal to 50. Now coming to the design steps. What is the first design step? The bearing length of the sitting plate is determined. So B is equal to that value. So B is determined, that value. Now from the length of the sitting plate is assumed, and it should be B greater than B plus C1. Now B has determined 178.82. Now assuming the length of the sitting plate, consider we are assuming the length of the sitting plate 190, it should be greater than that value. So 190, so it should be greater than 178.82 plus C1, assuming C1 is equal to 10 mm. So then it becomes 188.82. Okay, so it will become 188.82. So B is 190. So first criteria is satisfied. Then the width of the sitting plate, that will be equals to greater than the width of the beam flange. So what is the width of the beam flange? What is the width of the beam flange is for a ISMB 350, that is the beam flange. It is the beam flange is 140 mm. Okay, so it should be greater than that, providing width of the seat plate 160 mm. So providing the width of the seat plate, that is the width of the that value. So that value to be 160. Now coming to the second value, the second step. What is that? The second step is width of the seat plate we have determined. Now coming to the thickness of the stiffened plate. The thickness of the seat plate. Thickness of the seat plate is equal to greater than thickness of the beam flange. Thickness of the beam flange, it is 14.2. So providing thickness of the beam flange, providing thickness of the, sorry, it would be also mistake 1. So the thickness of the sitting plate equals to 16 mm, that we know. So now coming to the thickness of the stiffener plate. So we have adopted, so we have determined the thickness of the thickness and width of the sitting plate. Now the thickness of the stiffener plate is should be greater than 8.1 mm. Okay, the thickness of the beam wave that we know. So providing 16 mm. So it will provide it is a bit thicker, so as to provide same thickness as in the case of the stiffened seat plate. Okay, it is a normal thumb rule that we have adopted. Now coming to the this step, that is equals to d by t should be less than 18.9 epsilon for the buckling criteria. So d by 16, that is the t you have provided, 18.9 epsilon is equal to 1, so d should be less than 302.4. so d providing d is equal to 300 mm. It should be 300 mm. Now step 4 is E is equal to, so the eccentricity distance you have to determine b minus b by 2, that is equal to 100.59 mm. Bending moment we have calculated, we have to determine, that is 320.10 q, that is the value of the load, into 100.59 that we have determined. Now coming to this important part. So first we have to determine the value of the y1 dash towards the top. So value of the y1 dash will be, putting all the values here, BP, TP, D and TSP we have determined. Putting all the values written here, we can determine y1 dash equals to 120.96 and y2 is equal to 300 minus, so d minus that will be equal to 170.04. Now the term TT square will be neglected. So now all the value of the y2 has been determined. Now coming to the Ix6, so putting all the values here, we have got 711.29. Now here you can see there is a term called TT cube. This term will be neglected because consider the whole section, the value of the TT cube is a very not eligible term. Okay, it can be neglected. So the value of the TT cube can also be neglected, then TT cube will be 0. So that term will be 0. So putting the value, all the values here, that term will be neglected. Putting all the values here, we are getting the value that. So putting the value q1 and q2 from these two formulas, you have got these two values. Now here always the TT is, here always the TT, okay, here always the TT is, all right, 1 minute. So here always, here also TT has been taken common, so here TT is, we have to find out. So from here we can determine TT is equal to greater than equals to 3.67 mm. So TT is equal to 3.67 mm. Taking the value, it should be greater than or equals to, from this formula we have taken the value. If you use TT here, so TT should be greater than equals to that value. So size of the weld 5.25, providing 6 mm weld size. So providing a nominal weld cleat angle that we have to assume 100 into 10 into 6 and connected with a 6 mm weld. The same weld thickness has been used here. So we have used all the procedures, all the steps and determine the value. Okay, so this is the stiffened seat connection. Now coming to bolt bracket connection, the most important connection. Basically most of the math in your exam will be coming from the bracket connection. Okay, so you have to know very clearly about bracket connection. As in the case of bolted bracket connection, welded bracket connection also has two types, bracket connection 1, bracket connection 2. So bracket connection type 1, in case of bracket connection type 1, the twisting moment is in the plane of the weld. That means here the load is acting and moment is acting here. So the twisting moment is in the plane of the weld. The weld group is subjected to direct shear and torsion. Now therefore the welds are assumed to be located at the edge of the fillet. That is the edge of the fillet. Fillet connection. So always a fillet connection is selected and it should be at the edge of the fillet connection. Now the design procedure, we have to determine first the distance of the centroid of the weld group from the edge of the bracket plate. That means that this is the centroid of the weld group, centroid of the only weld group from the edge of the bracket plate, that to be first determined. So first we need to determine the value of the x dash. So let the distance be x dash. Now taking moment at the end, so we are determining the moment at the end. So we have to determine the centroid distance from the bracket edge of the bracket. So putting all the values, we know how to calculate the value. So here it will be L2 into TT into 0, because 0, why it is 0? Because L2 into TT is the area, and as we are determining at that place, so it will be 0. So putting all the values, we can determine the value of the x. Now where TT is equal to the thickness of the weld, throat thickness. So from here we can use, So Tt, if you take common from those two places, the Tt will be cancelled out. We can determine the value of the x dash. Now the polar moment of inertia to be calculated. What is the meaning of polar moment of inertia? Polar moment of inertia is equal to Ixx plus Iyy of the weld group. So Ixx is calculated. You can calculate the Ixx from the following formula. I have determined the formula. You can also determine by yourself how to determine this from the weld group, and then the Iyy also determined from this formula. Now here also Tt cube, here also Tt cube, as it is irrelevant to our welding connection. So the term with the Tt cube can be neglected. So this term and this term is taken as 0 because it's to be neglected. Clear? So this to be neglected first. Now coming to step number 3, direct shear stress has to be calculated from this value, R by 2 into L1 plus L2. What is L1 plus L2? L1 is the length of the weld at the bottom. This is L1, and this is L2, length of the weld at the side. Okay, so R1 into 2 into L1, that is the 2 into L1 plus L2, that is the LW, that is the length of the effective length of the weld, into Tt, that is the thickness of the weld. Shear stress due to twisting moment is calculated by R into E0 by R, that is by Ip. Ip is the polar moment of inertia that we have determined. Okay, then putting all the values of the formula E0, that we E0. What is the value of E0? Distance of the CG of the weld to the application of the reaction force. That means from here to the application of the reaction force, from here to here, this is E0. So we have to determine E0 also. Then and the R is the in the bracket connection that I have discussed in the bolted connection also, the R is same, the distance from the extreme weld from the CG of the weld. So this is from here to here, this distance is R. Okay, so also R to be determined. So R, for determining all the R, combined stress QR is to be determined by this formula. It should be less than that value. Cos theta is equal to, if we know here this is the value of theta. So if this is theta, so this is theta. If this is theta, then this is theta. So if this is theta, this is the base and this is the hypotenuse. If we want to find the cos theta, so base by hypotenuse, so that distance equals to, this is L1 from here to here, this is L1, right? This is L1. So L1 minus x dash, that is equals to L1 minus x dash divided by R, that is the hypotenuse value we know. So we can determine cos theta. Gamma mw we know 1.25 for shop and 1.5 for site welding. So from the above equation, site weld is determined. Okay, so S equals to, so here we know we do not know the value of Tt, that we have to find out Tt. So from the here we can determine the value of the Tt. Then from Tt we have to determine the size of the weld. Let us say one example. Again, let us open the procedures. Okay, so first step number 1. What is step number 1? First, the distance of the weld, distance of the centroid of the weld group from the edge of the bracket. So first is x value to be determined. Now here that value will be 0. So putting all the values here, L1 into Tt by T2, all the value. So Tt. So if we take Tt common here, so Tt will be cancelled out. So x dash equals to 60.61. Step 2, Ixx, that is equals to, we have to calculate the Ip, that is the Ixx plus Iyy. So Ixx, putting all the values here, we can calculate the Ixx, and Iyy by putting all the values. We know, you know how to calculate the Ixx and Iyy. We have used the formula of parallel axis theorem to get that. So putting all the values Ixx and Iyy, polar moment of inertia is determined by this formula. Now step number 3, we have to determine now here also you can see the Tt cube. These two terms are neglected here. So there is no these two terms. So these two terms has been neglected. Now here then comes the step number 3, Q1 and Q2. So putting all the values, Q1 is determined by like that. Okay, L1 equals to, in the math it is given that L1 equals to 200 and L2 is equal to 260. I have written all that also. So putting all the values here, and now coming the R. So R will be from here to here, Now from here to here is equal to r. Now this is the value of x dash, so that will be value of 200 minus x dash, because r equals to, what is the value of r? R means, if we see distance from the extreme weld from the SAG group, so L1 minus x, that means L1 is 200, so 200 minus x, that is 200 minus, where it is 200 minus 60.61, that is the value of r, and it should be, and the second one, that is the value of, okay, so r1 plus 2 into what it is, r1, so we have got the value of r, so this is r, okay, this is the value of r, and this is 260 by 2, so we have got the value of r. Now E is equal to, this value is E, okay, this value is E, so E is equal to, from here to here equals to E, so we can determine the value. This is 80, it is given in the map, this is 80, so 80 plus that value, that is 200 minus x, putting the value here, we can determine Q2 here also. So combined shear stress Q1 plus Q2, putting all the values, we can get 546.99 by TT. So cos theta we have determined. If this is theta, so cos theta is equal to, this is theta, so this is theta, so this is the base, this is the hypotenuse, so base equals to 200 minus x bar. So putting all the value, all the value we have calculated, so TT equals to, we are getting 2.89, so TT is equal to 2.89, we are assuming it should be greater than or equals to 2.89, so TT is equal to 2.89, S equals to 2.89 by 0.7, it is 4.13, taking a 6 mm, providing a weld size of 6 mm. So this is the bracket connection type 1. So always our motto is to design the weld connection. Okay, how to design the weld connection? We do not know the thickness of the weld, so we have to design that. Okay, so this is bracket connection type 1. Now coming to bracket connection type 2. It is similar as in the case of bolted bracket connection type 2 here. So here the moment in a plane perpendicular to the weld. So moment here, so moment is acting here. Okay, moment is acting here. It is perpendicular to the plane of weld. So this is the plane of weld. So it is perpendicular to the plane of weld. So design procedure. First, the size of the weld to be assumed is equal to S for fillet weld. For fillet weld, the size of the weld is assumed. Here, in case of the bracket type 2, bracket connection type 2, the connection may be either groove weld or fillet weld. Okay, so we can be, the connection can be determined for groove weld or fillet weld both. Now for the butt weld, that is the groove weld, effective throat thickness TT, that is the thickness of the thinner plate. If you can recall, I have also written in your previous notes, that is the thickness of the thinner plate to be taken when to calculate the effective throat thickness for complete penetration. We are taking complete penetration, and for fillet weld, effective throat thickness is equal to K into S, that is a 0.7 into size of the weld. Okay, so 0.7 we can take the size of the weld we have taken for fillet weld, so we can use the value. So for fillet weld, this is step number 1. Now step number 2 is depth of the bracket plate is determined. For butt weld, D is equal to that formula, where M is equal to R into E. R means reaction force and E means from here to that distance equals to E. So we can know the value of R and E, we can put all the values. Now FB is equal to Fy by gamma M0 for only butt weld, and here this is the formula for the fillet weld. If you put the value, FWD is equal to 0.8 into Fu by root over 3 gamma M1. So putting all the values, we can determine the value of the D, that is the depth of the bracket plate, that is the depth of the bracket plate for the connection. We can determine the value. Now step number 3, calculation of the direct shear stress. Q calculated. Q is the calculation direct shear stress. This is the formula. Now for fillet weld, R by 2 LW into TT, and for butt weld, R by LW into TE. TT means the thickness, throat thickness of the fillet weld, and T means throat thickness of the effective throat thickness of the butt weld. Okay, so putting all the values, LW is the length of the effective length of the weld. So now step 4 is equal to calculation of the weld. Now effective length of the weld. What is the value of the effective length of the weld? Here, if the length is there, this is the length of the weld, this is the length of the weld. Okay, because the welding is done on that part and that part in case of the fillet weld. So length, so here in case of the fillet weld, it is 2 into LW, because this is LW and this is 2 into LW, that is the length of the fillet weld. Now this is the calculation of the direct shear stress. Now the step number 4, calculation of the bending stress, fillet weld and butt weld. For both are there, two formulas are there. You can see this formula and this formula is similar. Okay, so you can see that this formula and this formula is similar. So putting all that, This is the formula. LW and LW square we know now. Then the E0 is the eccentricity of the load that we can know, that is the eccentricity. We can determine that we in the math it will be given the eccentricity of the load here. Now coming to the step number 5, equivalent shear stress. Equivalent stress is determined from the following formula: FB, either FB or FA. So if for fillet weld we have to use FB, and for butt weld we have to use F. Fillet weld we have to use FB for butt weld, and for fillet weld FA for fillet weld we have to use. So either value we can use, and 3 into Q cal. So Q cal also 2 Q cal has been calculated either for fillet weld or for butt weld. So this value can also be determined. So it should be less than Fy by gamma m0 and also Fy by root 3 gamma m0. Okay, so these two values has to be determined. Okay, so Fy by gamma m0 and Fy by root 3 gamma m0. Okay. So this is for butt weld and this is for fillet weld. This condition to be satisfied. Okay, from there the equivalent stress is calculated. Now coming to the math. So again let us open another window for the design procedure. Okay, first the effective throat thickness is determined. Now calculation, design the weld. Now for this is to be designed. Now let us assume fillet weld. We are designing the map for the fillet weld. Okay, so for the fillet weld, now what is the first for the fillet weld? The size of the weld to be assumed. Let us assume the size of the fillet weld. Now let us provide a 6 mm weld size. Consider we are providing a 6 mm weld size. Let us assume. Okay, so effective throat thickness to be determined is equal to 0.7 into 6, that is equal to 4.2 mm. Effective throat thickness will be 4.2 mm. First effective throat thickness, that is the calculation of the effective throat thickness, K into S. It is 0.7 into size of the weld. This is we are getting. Now coming to the step number 2. Step number 2 is depth of the bracket plate. For fillet weld, this is the formula: T is equal to 6m by 2 into TT into FWD1, where FWD1 is equal to that value. So putting all the values here, you can see we are getting 256.9. It can be taken as 260. I am taking it as 260 mm as the depth of the bracket plate. Now calculation of the direct shear stress, that is the step number 3. For fillet weld, the formula is that formula. That is the formula for the fillet weld: R into divided by 2 into LW, that is the length of the fillet weld, that is the we have calculated length of the fillet weld, we have to see and TT, that is the throat thickness. So after the throat thickness we have calculated, is 4.2. Now coming to the length of the fillet weld. Now this formula I have told you, the length of the fillet weld will be always equals to that thing. This is the one length of the fillet weld and this will be the another length of the fillet weld. So length means the depth of the fillet weld. The depth of the bracket plate is the length of the fillet weld. So putting the value of the LW here, okay, putting the value of the LW, that is the D, that is the length of the calculation of the bending. So LW is equal to the length of the fillet weld. So equivalent stress formula. So then formula for the equivalent stress. Okay, the calculator for the bending stress here, the formula is similar. I have shown you that this formula and this formula is quite a bit similar. So putting the values here, we can get that the value of the these two values are the same, will be coming. So equivalent stress will be that it should be less than that value. So you can see that it is less than 189.37. So this is done. So in our lecture, today's lecture, we have seen how to design a weld. So basically design means the design of the connection, that is the weld connection has to be designed. So basically we have seen, first we have assume a size throat thickness, is the TT. We have taken we have taken the TT as TT, then using the formulas we have calculated the value of the throat thickness, and the last case, that is the last bracket connection, we have assumed the throat thickness. So this is the welded eccentric connection. So proving all the formulas, we can get all the maths. Okay, please follow it very carefully, because welded and bolted eccentric connection is very much important for your math, and it will come 1 or 2 maths from welded or bolted eccentric connection will definitely come in your exam. So follow all the procedures written here and do practice the math for your thing. Okay, so goodbye for now. In the next class we will discuss the last chapter that is remaining, that is the plate girder design. Okay, thank you very much for your time class. Okay, thank you.